So I'm going to be, so this presentation is going to be about 20 minutes. And I'll take some time to introduce the problem and set it up, and then get into some technical details through the middle of the talk, and then present some simulation results towards the end. Please feel free to stop me at any point, and then we can discuss more if something is not clear. So this talk is mostly about how to localize sketching, like how Jacopo mentioned, and this is joint work with my advisor Justin Romberg and my close collaborator Mark Davenport. So I want to begin by sort of introducing what sketching is and why it's such an important tool when we deal with high dimensional data. So we all of us are familiar with the difficulties associated with high dimensional data. So even very basic algorithms like least squares regression can get easily overwhelmed when the data lies in very large dimensions. And I think going forward, it's quite conceivable that in all applications, the size of data is only going to grow. So we need methods that or algorithms that can scale to such large data. So one solution to this problem is called the sketch and solve paradigm. So when it's difficult to compute with or communicate high dimensional data directly, what the idea suggests is you sketch or compress the data to a lower dimensions, and use the same algorithm that you would have used before on these in these lower dimensions, and perform inference or communicate the data, and then also give sort of an approximation guarantee on how well you can do, depending on how much of dimensionality reduction has been done. And many standard examples of this workflow lie in the area of compressed sensing, and even the famous Johnson-Lindenstrass lemma is also a very classic example of this idea. So with that background in place, in today's talk, we'll only focus on linear sketching. What do I mean by linear sketching? So if we have a high dimensional vector, we are going to hit it with a randomized underdetermined matrix, and that's going to take our high dimensional data into much lower dimensions. And now we are going to work only in the lower dimensions. But then I would like to point out one standard assumption that a lot of existing sketching methods make. And that assumption is that we either have access to all of the data points at a single location, or if not, we need access to an arbitrary subset of the data points. So for example, one way to do sketching is to just hit it with a random Gaussian matrix and take a few random projections. But then to take each of the random projection, we can see that we need access to all of the data points. And this might not be feasible. And there are also something called sparse sketches, which are known to be very fast in how you can apply it to data. But then you can't really control the subset of data that you need to compute each of the random projections. So this is sort of a difficult, this sort of a difficulty associated with these sketches, in the sense that these methods are designed for large data sets. However, they need all of the data to be in one place, or at least arbitrary subsets. And this is not always possible, especially in large data regime for which these methods have been designed. So there is a sort of a mismatch between existing methods and a lot of applications where data is sort of naturally distributed. And to just point out a few applications where data is naturally distributed, let's go to this application called square kilometer array. And this antenna array has antenna elements spread across 2 continents, like Africa and Australia, and all of them are collecting a lot of data to generate high resolution astronomical images. And the data rate is expected to go up to 157 terabytes per second. And this rate is actually 4,000 times the rate at which data is uploaded to YouTube. So you can imagine the scale of the data that's coming in. And first of all, it's very difficult to apply any algorithms directly on this large data. So we will need to use some sort of a dimensionality reduction before we do anything with this data. However, it's also difficult to assume that all of this data can be stored in one place where we can apply a dimensionality reduction mapping. And that is where sort of this assumption breaks down in applications like these. And some other applications are, again, airborne sensor systems where you have a lot of communication constraints. So you might not be able to communicate all of the data you're receiving, and you might want to reduce its dimension and then send it across. And another example is cloud architecture, where you have a lot of devices collecting data and sending it to a cloud. And in all of these applications, a common feature is that they have a certain underlying low dimensional structure. If they're truly high dimensional, then there's not much we can do anything about it anyway. But in sort of these antenna array processing systems and cloud-based systems, we can always expect them to have low dimensional structure. For example, in an antenna array, it's the number of degrees of freedom is usually equal to the number of objects you're trying to take a picture of and things like that. So there is a low dimensional structure associated with this data. The question is, how do we take advantage of that? So let me just pause for a second and ask if there are any questions so far. Right. So the idea is that we have a lot of data and it's distributed in a lot of places. How do we perform dimensionality reduction? So our answer to this problem is that we need to impose a particular structure on our sketching matrix. And henceforth, I'm just going to use the term sketching matrix to refer to just a dimensionality reducing map, a linear dimensionality reducing map. So previously what we saw was this matrix on the left here could be unstructured and drawn from any arbitrary random distribution. But then that we ran into problems. So what we're now going to do is enforce a block structure onto this randomized matrix. And what is the advantage of doing this? So we can see that the top block of this diagonal matrix just needs access to this top block of the data matrix itself. So you can think of this as one antenna element on collecting the top block of the data. And we are going to reduce the dimension just by using that subset of the data itself. And we're going to do that at each sort of node which is collecting data. This way, we are going to still reduce the dimensionality of the data, but we're only going to do it using localized sketching. And but then obviously now this is very different from doing sketching with dense random matrices. So the main question is, since we are getting this advantage of being able to sketch it locally, what are we going to pay extra? What is the price we have to pay? And we are going to look at this in two specific problems. One is in computing approximate matrix multiplications, and the other is in just a simple least squares regression problem.
Excuse me, may I ask a question?
Yeah, definitely.
In your diagram here, the small matrices, they seem to be identical, the four submatrices in the diagonal. Is it by design, or is it just the way you drew it?
It's just the way I drew it. It actually should not be the same, because if they are different, then we are inducing more diversity in the way we collect measurements. So that's something that I need to correct in my figure. So they're actually different random matrices.
Okay, thanks.
Yeah, and another thing that I need to point out is also that they are also of different sizes. So maybe here I'm giving an impression from the figure that they're all of equal sizes, but we will see that in order to sort of in order to be the most sample efficient, these blocks will need to be of different sizes also. And I apologize for not sort of depicting that in the figure. But so they are different and they're also of different sizes.
Thank you.
I hope that clarified.
Yeah, absolutely.
Yeah, thank you. Yeah. Okay, so now let's dive into the first sort of problem, which is approximate matrix computation. So it will start to get a bit more technical from here, and so please feel free to stop me and ask questions. So let's assume that we have two very tall matrices, W and Y. Both have a common height of n tilde, and they have W has a width of m, and Y has a width of p. And the task is to just compute W transpose Y, which is going to be this small matrix M cross P. Just a second, let me move this window. Yeah. So can you guys also see this window?
No,
yeah.
we only see the slide.
Okay, perfect. It was just on my end then. Okay, great. So so the task is just to compute this W transpose Y. And if you just do it naively and directly, the order of computation is of the order MP n tilde. And then when n tilde is very large, let's say millions, this can be difficult to do. And especially when we need to perform these kinds of computations over and over again in optimization algorithms, let's say, it builds up, and the computational cost can be massive. So the idea then is to first sort of hit Y and W with a compressive random matrix on the left, and take the dimensions from n tilde to m tilde, which is now much smaller. Now, something that I'm sort of sweeping under the rug here and not really addressing is how much time it takes to compute this sketch itself, right? So if that time itself is sort of as big as the time required to compute this original product itself, then sort of there's no point in doing that. But then there are sort of methods that can compute this sketch very quickly, first thing. And the second thing is, we only need to do this once. We don't have to do it over and over again in, let's say, iterative algorithms and so on. So the idea is then to use a dimensionality reducing map first on these matrices, and then multiply only these small matrices to compute this product. And our goal is to do this in such a way that the final product, which is now going to be SW transpose SY, it should be close to our original product in sort of a relative spectral norm sense. So the error is going to be within an epsilon of the product of spectral norms of W and Y. And the question of interest here is, how big does M tilde have to be? And we already sort of know this answer when the sketching matrix is not block diagonal, but we don't know how big it needs to be when this is block diagonal, and if we have to pay anything extra. So that's what we're going to look at. So just to make the notation a bit more formal, whenever we are going to use block diagonal matrices, we're going to denote it using S subscript D, and it's going to have J blocks. And each block is of so the jth block is of size mj cross n, which means that its width is n and its height is mj. So it's going to be applied to the data block. And we also are going to assume that there are j data blocks. And each data block is of the same size n. So we're going to take this block, let's say A1, run it through S1, and we're going to get something that's of height M1. And the hope is that M1 is going to be much smaller than N. And another quantity of interest is the total sketch size, which is basically the height of this matrix SD. And that determines overall how much of dimensionality reduction has happened. So I'd just like to pause here for maybe a few seconds to take the notation in, because we're going to be using that going forward. So our data matrix is N tilde tall. It has J blocks. Each block is N length. So Jn is nothing but N tilde. We're going to hit it with a dimensionality reducing block diagonal matrix, and the total reduced dimension is going to be M tilde. So we just need to remember what these numbers are going forward, right? So now the main question for this matrix multiplication question is, can M tilde be proportional to the inherent dimensionality of W and Y? And what is this inherent dimensionality that I'm talking about? So usually the dimensionality of a matrix is captured by its rank, but we are going to be a little more strict about it and say that we are going to use something called a stable rank. Now, a stable rank is nothing but a proxy to the rank itself, and takes into account that the singular value spectrum of the matrix can have a quick decay, which means that even though technically these matrices are full rank, they might have a very small rank. So what we want to do then is to see if our reduced dimension can be sort of proportional to just the stable rank of these matrices. And to answer this question, we will need to define one more quantity, which we will call the incoherence. And what this incoherence captures is the relative importance of different data blocks. So as I said before, we assume that our data matrices are partitioned into J blocks, right? Now, some of these matrices might be more important than the others. And in an extreme example, let's say one block is just zeros. And then if it's just zeros, we don't want to draw any random projections from that block. But then, so the rest of the blocks become more important compared to the zero block, and we would want to draw more random projections from those blocks. So this sort of relative importance of these different data blocks is captured by this term incoherence. And how do we define incoherence? So we first concatenate these two matrices W and Y and take an ortho basis of this concatenated matrix. And then we can also divide that into J blocks because it's of the same size as W and Y. Now the incoherence is going to be defined as this quantity that I'm showing on the slide. So basically we can think of this gamma uj as a proxy for the energy contained in the jth block of this ortho basis. This is a bit technical, but like I said, it captures how much importance each of these data blocks carries, and we can just think of it as the energy present in these different blocks of these ortho bases. Now I will say that we might or might not have to compute these ortho bases to compute these incoherence terms. And how to compute these incoherence terms efficiently is a completely like a new question. And right now we only have a heuristic algorithm for it, and like formalizing that algorithm is still an ongoing work. But something that I would like to point out, and something that is enough to take away from the slide, is that all of these gamma parameters are going to be between 1 by j and 1, where j is the number of blocks itself. Now, with all these quantities defined, what we're going to do is design this sort of block diagonal matrix in such a way that each block whose size is mj, so the entries of these blocks are going to be drawn from a Gaussian random distribution, and the size of the block matters a lot. So the size of the block needs to be proportional to the stable ranks over epsilon squared, where epsilon is sort of the tolerance. And it needs to be multiplied by this gamma parameter itself. So for example, if some block has a high importance parameter, then we are going to draw more random projections from that block. And then if we design this block diagonal matrix in such a way, then we are able to achieve this epsilon norm guarantee that we wanted. And so what is the takeaway from this slide? So for incoherent matrices, by which I mean sort of the energy is well spread out across all these different data blocks, and these different gammas are all of the order 1 by j, their sum adds up to 1, which means that the total sketching dimension adds up to just something proportional to the stable rank over epsilon squared. And this bound on the right hand side is exactly what is achievable even with sort of these dense sketching matrices which don't have these localized sketching property. And so the fact that we are able to achieve the same bound for block diagonal matrices is sort of a very good thing, because it says that even though we are doing this in this distributed manner, we are not losing much on the total sample complexity. And with this background, we are also now ready to talk about, maybe quickly, the ridge regression problem itself. So again, I'd just like to remind what the ridge regression problem is. And it's just this least squares optimization, where we also penalize the energy in the covariate vector itself. So we want to solve this first equation on top. But then so I've sort of not used, denoted the sizes of A, but we can again think of A being very tall. So as the size of A increases, solving this problem becomes more and more difficult. So again, the idea is that we first drive down the dimensions of A and B to a much smaller dimension, then just solve this optimization in the smaller dimensions. And what is our goal here? Our goal here is that if we compare the two solutions, so X star is what we would have gotten by solving the full problem, and X hat is what we get by solving the smaller problem. We want the final objective function value to be within 1 plus epsilon of the true objective value. So obviously, the f of X hat is going to be larger than f of X star just because of optimality of X star. But then we want it to be as close as possible. And we want to do it in such a way that the dimension in which we solve the problem is close to something called the statistical dimension of the problem. And again, this is just a proxy for the rank of this matrix A, and again is upper bounded by rank of A. So if A has like a decaying spectrum, then statistical dimension is sort of much lower. And again, the sort of a quick overview of our result is that if we design this block diagonal matrix such that the sizes of these different blocks are proportional to the dimension itself multiplied by this incoherence parameter, then we are able to sort of get to an optimal dimension while also achieving an epsilon norm guarantee. So the summary so far is that if we design this block diagonal matrix in a correct way, then we are able to get sample optimal sort of sketches that give us epsilon good solutions. Some simulations to show that our theory actually works. So here what I'm showing is the solution to a ridge regression problem, where the blue line is the sort of the relative error between the true solution and the sketch solution with a dense Gaussian sketching matrix. So the blue line sort of is sort of what we can do, what can be done in an ideal situation where we don't have to do this localized sketching. And the red curve is a block diagonal matrix where these block sizes are just uniform and not designed according to these incoherence parameters. And we can see that in order to achieve a very small error, it needs a lot of sketches, which is basically the y-axis. But the yellow line sort of matches really well with the blue line. And the yellow line is a block diagonal matrix that has been designed using these importance parameters. And we are able to get very low errors very quickly. And this toy problem was of size. So the matrix was of size 20,000 by 50. We had like 10 blocks and each block was 2,000. But obviously the results will be more and more dramatic when we work with bigger and bigger matrices. And in this case, the rank was 50, but the statistical dimension itself was about less than 10. So the takeaway from this figure is that block diagonal matrices can be as good as dense matrices, but we need to design them a bit carefully. And another plot that I wanted to show was, so this plot was on synthetic data. So we just synthesized these matrices on our computer. But then we also tried this on a real data set. This data set is sort of, so it has a lot of features of different songs. And given access to these feature vectors, the task is to predict which year the song was sort of released in. And it's just, again, a ridge regression problem. And what I'm showing here is two phase transition plots. The top, so the x-axis is the sketching dimension, or the number of sketches we take, and the y-axis is sort of the accuracy. And the top figure is for dense sketching matrices, and the bottom is for block diagonal matrices. And if we design it carefully, we see that the phase transition is exactly matching. I know I'm sort of a little over the time, so I'm going to quickly finish.
Sorry, Rakshith.
Yeah.
You hear me? About this plot, I would like to ask you a question, because
Sure.
I read your paper. I found it really interesting.
Mm-hmm.
And I remember on your paper, the x-axis is the m tilde.
Yeah.
And the epsilon axis is epsilon, right?
Right.
And honestly, one of the things I was wondering is that, for example, I mean, I saw this quite often done in sketching papers. Is like,
right.
But why, for example, when you use a data set like here prediction, for example, not to show like the accuracy or like the generalization accuracy?
Mm-hmm. So can you repeat the question again, please?
Like, for example, here you are showing the probability that is below epsilon, right?
Right, but, exactly, yes.
But for example, what about the train accuracy and the test accuracy on such a data set?
Sure. That's a great question. So, right. So what we're doing here is, let's say you solve the full system, right? Yes. Without doing any sketching. You get some generalization accuracy, some training accuracy, and some test accuracy. So these are metrics that you can get for the full system. Now, what we are showing here is, let's say you sketch it, and so after sketching, let's say you fix an epsilon of 0.2. So all the accuracy metrics will be within sort of 1 plus 0.2 of that of the metrics that you had originally anyway. So that way, whatever generalization accuracy we would have gotten with the full system, we are able to get very close to that using the sketching system. So that's why we sort of look at this probability that it's within the epsilon.
Okay, thank you very much. And another question, I was trying to recreate this plot on the same dataset, and probably it's my fault, but I didn't find the J you used, because, for example, in this dataset it's not divided. But
sure. Probably don't have it mentioned in the paper, but I can definitely get back to you on that, sort of look into my code and maybe even share my code with you, so that we can see what J is. But I think in my another sort of idea is that it really doesn't change much with J, so we can just experiment for different parameters of J also. But I'm more than happy to look into my code and let you know what value of J I used.
Okay, thank you very much.
So please, like, let's connect offline, and then I can definitely share that information.
Thank you.
Yeah. Okay. So moving on, something that I spoke about a little bit initially, but didn't really touch upon during the rest of my talk, was how much time does it take to compute these sketches itself, right? So if that is the dominating factor, and it sort of needs more time than doing the original task itself, then there's no point to this. But then we got pretty exciting results when we looked at the sketch compute time itself. So let's say you have a tall matrix, where by tall I mean the size is indicated on the left here. So for example, a million with 2 to the 20 is a million. So you have a million tall matrix, and I think the width I used was 40. So these are all million by 40 matrices. And we want to reduce it to a smaller dimension, let's say 600 to maybe 3000. And we have a lot of blocks here, maybe like 1000 to 4000 blocks or so. So what existing sketching methods do is sort of use something called the fast Johnson-Lindenstrass transforms. Basically, all that means is we are able to reduce the dimension in an order of time that's proportional to taking a Fourier transform. So what we did was compare our block sketching directly with the Fourier transform applied to these tall columns of these tall matrices. And at least for the parameters that we are considering right here, we are able to do it much faster than a Fourier transform itself. However, there is a caveat. So you can notice that Fourier transform takes the same amount of time to sort of compute these sketches for all sketch sizes. So if we want to really compute a large sketch size, then maybe Fourier transform is going to be faster. But inherently, sketching is always like going into lower dimensions. So there's a lot of hope in that these block matrices can also be applied very fast to data matrices. So sketch compute time itself isn't very large. So that brings me to the end of sort of everything I had in this paper. In the next maybe 10-15 seconds, I just like to point out two other sort of sketching problems that I have worked on, and would be very happy to talk about those also. So another problem where this block diagonal structure comes into play is if we have a low rank matrix that we want to sketch and sort of recreate at a later point of time. We can sort of sketch each of these columns down to smaller dimensions. And we have a method in this paper that I've mentioned at the bottom, where we can recover this low rank matrix from these column-wise sketches. And you can think of these columns as sort of states of dynamical systems that are coming in one after the other. And you don't want to store the entire column. So you want to sort of compress it and store only the compressed values. If they have a low rank structure, we have a method to sort of recover those matrices from these column-wise sketches. And another problem that I'm really excited about and have been recently working on is graph neural networks, where if you have really dense graphs, very large dense graphs, graph neural networks take a lot of time to get trained on these graphs, and sometimes can even just run out of memory even on large machines. So an interesting problem is to sketch or sparsify these graphs, basically retain just a subset of the graph and then train the graph neural network just on the subset of the graph and sort of achieve a similar generalization accuracy. And I sort of have a first step in this direction in this paper that we just uploaded a couple days ago. So that brings me to the end of the talk. And I wanted to say thank you in French, but I think I'll do a really bad job. So I'm just going to say it in English. So thanks a lot for having me. And this was really nice.